Hi, my name is Ryan Thompson, and this is my submission for question 6 of the CPSC 5210 final exam. In question 6, we're to illustrate the application of dynamic programming on the HCS of X and Y matrix, or on the X and Y given the above matching matrix. So to illustrate the dynamic programming, I implemented the X and Y strings. Here's X, B, C, B, A, C, B, A, D, C, D, D, and Y, B, C, D, A, B, C, B, D, D. So, and this index just looks a little off because of the copy and pasting. But so to illustrate the this heaviest chain here, the part of dynamic programming is to incrementally go through and evaluate, does this match? If this matches, check the upper corner and add to whatever the weighting is. If it's a 1, if it's a 0, or some other value. It can be integer, non-integer. That's fine as well. And so you can see as you go through and you check each one, you have to say, is it equal to its predecessor? If not, or if B does not equal B, then look to the left or look to the right, depending on which value is greater or not. So this is an illustration of how we incrementally go through to match and then check the next string. Does B match C? Answer's no, so you'll pull from the left, bring it over. Same thing, B match D, nope, pull from the left, bring it over. And so you'll keep performing this operation as well. And here you can see how incrementally it builds up to find the maximum submatching string here. So you can see where each one matches in a row and where each one does not match in a row, and how that will articulate through. So then you have B, C, D. So B, C, D. Then you finally have an A over here, and then you'll have the next matching. But you can see how this builds on itself. So that's part of the dynamic applications, or the dynamic aspects, where you're breaking the problem into subproblems and then calling on the solution of different subproblems. So you've already determined for any iteration if element 1 matches element 1 between different strings. It does, so you'll put a 1, but you can always re-reference that value, and it's already been solved. So you don't have to find a new solution every time. So this diagram here really represents the this diagram here represents the direction for what value you're pulling from. So any diagonal arrow means we have a match and we pull the value down. Any up arrow represents here. Any up arrow represents that the iteration is greater than the current string. The prior iteration, I, is greater than the current string of J, and so you pull it up. And this here is just a bad formatting by the PDF, but it's supposed to be the left arrow. So this symbol represents pull from I minus 1, J minus 1. This represents pull from I minus 1. And this represents pull from J minus 1. So you're really searching for which value is greater. If you don't have a match, is this value greater than that value? If so, do this. If not, pull from the left. So you can see the direction arrows on what happens and how any value can matriculate throughout the entire matrix. So here's the scoring matrix, and on the numbers and how those numbers add up to what the maximum submatching string is. And then here's the direction, the indicator of where those came from. You have upper left, upper, or left. Left in this case. So that's the illustrated here is how dynamic programming solved this subproblem, and you'll call on that subproblem and bring it forward. So you've solved the subproblem, call on that subproblem, bring it down. Solve the subproblem upper, or you've solved the problem, evaluate it against the previous solved upper problem, and carried it down. Same thing here. Solved the problem, evaluated against the upper. It wasn't greater than, so you pulled from the left. So again, you've got these problems you've already solved, and now you're just comparing the results to a known result, but not having to go through the full calculation again, which could be lengthy or not. In the second subsection of 6, you're asked to design a HCS algorithm by modifying the LCS algorithm. So here I've labeled it LCS length mod, and it takes 3 inputs. It's got your X string, your Y string, and then your matching matrix. So we were given this matching matrix. So for any unique value of X and any unique value of Y, at their intersection, what is the value that's given to them? And it's not the same throughout. Some is 0, some is 0.5, some is 2, some are 1. Some of the intersections are 1. So given that matching matrix, however that was determined, we can feed that in. So here, m is equal to length, or m is equal to x dot length, n is equal to y dot length, k is equal to the number of columns in m. And because m is a square matrix, it works this way works. You're not going to undercount. And the column names variable is equal to the unique strings in m. And these unique strings are because the square matrix, these unique strings are at least all represented in x and y at some point. So at the intersection, or at the union of x and y, that's how you get the unique column names. Now I create 2 variables, x map and y map. And x map is dimensioned to the size of x, and y map is dimensioned to the size of y. And both start off empty. And then we're going to let the value b, be a matrix, and c be a matrix as well. And they're both new tables. So from 1 to m, you're going to set ci, the top row, equal to 0. And then for p equal 1 to k, if xi is equal to the column name, so we're starting at the first string, the first part of x, and we're saying if that is equal to the column name, if it matches x map equal p. So what I did here is I just created the indexing, the row index, or what will be the row index. And I loop through to find that. Now, for C, I do where I told the row, I gave it a row value, and J, now I give it the column value, or I set the column value equal to 0. And now I loop through again from 1 to n, and P equal 1 to K, where K is the number of unique letters to match. And if Yj is equal to column name P, then Yp, or Y map J, is equal to P. So now I'm creating the column index. So for any of the elements of Y, I know exactly where it falls in the matching matrix. So now for each unique element, I know the exact row and column index. So for I equal 1 to m, so now I'm going to loop over both y and x at the same incrementally. And I say if yi is equal to, if xi is equal to yj, if that's true, if they have that intersection, then I take the upper left value of that, the previous iteration, or the previous value of x and the previous value of y, and I add to it this, my mapping index. So I have my matrix, my scoring matrix, and before I built this row mapping, and then I built this column mapping. So now I index into M and return that intersection's unique value. And I add it to the previous one. Also, I give this directional arrow saying of where I pulled that value from. Else, if they don't match and the previous X is greater than the previous Y, or if the previous heaviest common string of X is greater than the previous the heaviest common substring of Y, then I want the heaviest one. So then I pull from X, which means it's the value up and it gets brought down. Now, if the previous Y is greater than X, then I pull from the Y value from the left. So you look for the match first, and then you say, was the previous X value greater? Lead me to a greater heaviest common matching string. If not, then I take the Y value and bring it over. So Y is the default one there because you're evaluating the other two conditions. So for me, the modification here is a way to incorporate the matching matrix M. And I feel that I achieve this, or I know I achieve it, but I feel like I do it in an efficient manner because you're creating the index early and you're already looping through all of C. And so you're adding in an additional K loop for every M. So M times K, and you're also doing it for N times K. So M times N times K, whatever that value is. That's a iterative loop added to this. Also, this indexing function doesn't change this loop at all because you're already doing that in the previous method. So really the additional overhead to incorporate in that matching matrix is this M times N times K loop that goes on. So however long it takes to evaluate here and whatever the index is, that's what you'll add to any runtime. So if K is large, a lot of unique values, that's going to increase quite a bit then, depending. But here, I think we only had 4 to begin with. So for me, the integrated trick is to create this row and column mapping match and then apply forward. And again, these arrows were reflected up here and they're reflected here. So these just give the directional component for which you're pulling from. And here is the commonality index, some quantitative number score to tell you what is the sequence of highest matching between the two sets X and Y.